I ask a lot of questions. Okay? I ask a lot of questions. I do expect answers. If you answer, you will get a football. If you ask a question, you may get a football. If you ask a stupid question, you'll get a football. There are no such things as stupid questions, right? The only stupid question is the one that does what? That goes unasked. Okay, so I want you to ask questions. You may get a football if you answer a question. You may get a football if you fall asleep. No, you will get a football if you fall asleep. Right between the eyes. All right? The answers to all the questions are typically in your book or on the board. As I said, we're not actually following that agenda. That agenda is for our 2-day program. We're going to go through the first presentation. We're going to go through the second to last presentation today. Okay, because we just don't have enough time to go through both of them. So, let's take a look at it. We're going to take a look at what it takes to make a chip. As I said before, our customers make parts. Okay, you make parts, right? I could care less about your part. What I really truly care about is making good chips. And I want to make good chips, and I want to make a lot of them. Because if I'm making good chips, I'm making a lot of them. Not only am I making good parts and a lot of them, I'm probably making money, which is important to all of us. We're going to talk about the basic elements in carbide. Carbide is the primary cutting tool. Are you guys using carbide or high-speed steel? You are using both? Both. Okay, we're going to talk about primarily carbide because carbide is what's being used primarily in industry today. We're going to talk about basic cutting tool geometry. And the reason we talk about carbide and the reason we talk about basic cutting tool geometry is because you need to understand how the cutting tool cuts. Right now you're learning the fundamentals of machining. Pretty soon, are you learning programming as well? Yeah. It's okay to know programming. It's okay to learn how the machine works, but at the end of the day, you've got to understand what's really happening where the rubber hits the road or where the cutting tool hits the steel. And that's what we teach. And the reason why we teach it, to get back to your question, you can't learn this anywhere else. They don't teach it as much in tech school. They don't teach it in the 4-year engineering schools. That's why it's up to us to do it. We're going to talk about cutting tool angles, lead, rake, and relief. We're going to talk about cutting forces. How many of you remember Star Wars? At all. What did Obi-Wan tell Luke to do with the Force? Use the Force. Here's the truth. When you're cutting metal, there's going to be cutting forces. They're not going to go away. What we want you to know is how to use that force to your advantage. Last but not least, we're going to talk about cutting versus rubbing. We're going to talk about productivity versus tool life. And then we're going to talk about basic machining operations. Now, when you look at these pictures on the right hand of that slide, which one do you think does not belong? Go ahead. The yin and yang? Oh, I missed. That was a horrible throw. Hey, watch it. Okay, he got it. The yin and yang. Why do you think it does? What does yin and yang stand for? Does anybody know? What's yin and yang stand for?
Balance.
Balance. It's actually yin and yang is good and evil. It's the balance. The symbol of yin and yang up here in the corner is the symbol of the balance of good and evil. And when you take a look at machining, the reason I have that up there is because in machining, it is always a balance between good and evil. If I change my edge prep on my cutting tool, there's a good thing and a bad thing. If I change my lead angle, there's a good thing and a bad thing. If I change the carbide grade that I'm using, there's a good thing and a bad thing. It's incumbent upon you to figure out what the good things and the bad things are, because that's part of what you're going to do when you troubleshoot machining operations as you get out into the real world. So in reality, this is the most important thing. So before we get started, it's important to understand in a metal cutting operation, what's really happening to the metal being cut? What's really happened to the metal being machined? Anybody know? By the way, the answer is in your book. They teach them to read at that school. They don't? Okay.
No, just text.
Just text? You know how to text, right? You can text me the answer, right? In a metal cutting operation, what's really happening to the material being machined, go ahead, is being plastically deformed. Sheared away is one of them. But this metal, in order to make this chip, we must first plasticize the material, and then we shear it away. At the shear zone, where the cutting tool is hitting the metal, it is 12 to 1400 degrees Fahrenheit. 12 to 1400 degrees Fahrenheit. How many of you knew that? So what we're actually doing is we're plasticizing the steel, and then by the feed force, we push it away and shear it away. All right? That's what's really happening. This is my cutting tool. This is my chip. This is my part. Right here where the cutting tool hits the part, that's 1400 degrees Fahrenheit. Let's take a look at what it really looks like up close. Here again, up there at the top, this is my cutting tool. This is my chip coming off. This is my part. If I drew a line from this corner right here at the tool, diagonally here, this is what I call my shear zone. Right there, it is 1700 degrees Fahrenheit, or 1200 degrees Fahrenheit. Pass this around. So when you look at the outside of this chip, that is the side of the chip that's actually rubbing what I call the rake face of the cutting tool, and we'll talk about that. The inside of the chip you see is undulating. See the bottom of this chip coming off? If you look at it, see how there's segments? You see those lines? That's really what's happening.
That's sharp. Just be careful, guys.
Yeah, don't cut yourself. Yeah, you could cut yourself. I would prefer you carry it by the wood. So, in a metal cutting operation, we're plastically deforming and shearing away the material. How many of you like butter? Seriously, I like butter. You can tell, can't you? Now, when you take butter, I'm not sure I like your answer. All right. Yes, I do like butter. My doctor doesn't like it, but I do. All right. When you take the butter out of the refrigerator, is it easy to cut and put on toast? No, it's not. It takes a lot of force, right? And when you take that butter and you start putting it on your bread, it rips up your bread. I don't keep my butter in the refrigerator. I keep it in the cupboard. I take my knife out and cut it. It cuts real easy, doesn't it? It makes it easy for me to eat more. Same thing's happening to the tool. Think about it. If I don't have enough heat at the shear zone, it's going to take more what? Force or pressure. If I have too much heat at the shear zone, what do you think is going to happen? Not only the part, what else is it going to melt? My cutting tool. All right, so what two things, if I'm plastically deforming it and shearing it away, what two things does it take to make a chip? Heat and pressure. It takes heat and pressure. If I'm plastically deforming it and shearing away, it takes heat and pressure at the shear zone. Now, how do I create the heat? It's friction. If you hold your hands together like this and you do this, what happens? You start getting temperature. It starts getting warm. Now, so, how do I create that friction? Well, the tool's running across this part, but think about it. The rotation of the tool or the rotation of the part, depending on whether I'm turning or milling. Make sense? Now, how do I regulate the amount of heat? Because remember, the amount of heat I create at the shear zone is just like Goldilocks and the Three Bears. You have to have surface footage, and it has to be the right surface footage. How many of you really don't understand surface footage? How many of you, all of you understand surface footage? Really?
There are teachers in here, they can't see.
No, that's right. How many of you use toilet paper? How many of you use toilet paper? You're not going to raise your hand? All right. Here, this is the best way if you're ever trying to explain surface finish. Think about it. If I had a small roll of toilet paper, I had a big roll of toilet paper. Your teacher back there is holding it on a broom handle. If I walked 100 feet in 1 minute, what was the surface feet of both rolls? The small one and the big one. 100 feet. Were they doing the same RPM? No. Which one was going faster, the smaller or big one? Smaller. Why?
That takes less.
Because it had a smaller circumference, and it had to go faster to get the same surface ripped off of it. Okay? It's all about having the same amount of material crossing your cutting tool in a fixed amount of time. That is how we regulate the heat. Do you run the same speed, surface feet per minute, for all materials? No. For every material, there's a thing called a machinability rating, right? And what that machinability rating, it's more complicated than what I'm going to say, but to me, what it means, that machinability rating, is the amount of heat and pressure it takes at the shear zone to plastically deform and shear away that chip. That's really what it's all about. Make sense? All right. So, it's all about, a lot of times you'll see it in industry, you won't see surface speed. You'll see velocity constant. Because in the United States, it's what? Surface feet. In Europe, and honestly, in America today, there's a lot of European manufacturers. A lot of people are using metrics on all their prints and on all their programs. So you have to start learning both. So we regulate the heat by the speed. How do we regulate the pressure? By the feed rate. It's all about the feed rate. And that's either in inches per minute in turning, well, no, inches per minute in milling, or inches per revolution in turning. How many of you remember this? Who was laughing? You don't like it.
I hate it.
I hated it too.
Now I teach it.
This is why I went into tech school instead of on to the physics track. You got one, right? All right, this is the periodic chart of elements, and the reason we show that is there are three basic elements that make up carbide. Three basic elements. What are they? Cobalt is one of them. Tungsten's another one. And carbon's one of them. So you got carbon, cobalt, and tungsten. Now, hold on.
If I have it's on the floor.
Is it on the table? Oh, you did. When I think of carbide, what makes it up? I actually think Rice Krispie treats. How many of you like Rice Krispie treats? All right. This is easy to understand with carbide. When you think about carbide, think about a Rice Krispie treat. Because what we do, there are two elements in carbide that we combine to make the Rice Krispie, or the hard wear-resistant molecule in carbide. What two elements do you think they are? He's getting all these right and he doesn't have his book open. Now he's stumped. Okay. What do you think they are? Tungsten and carbon. Think about carbon. What happens when you burn toast? It turns black. What is that black stuff? It's carbon. If any of you watched Star Trek in the old days, we are nothing more than carbon-based beings. If you burn me up, what am I going to turn into? Carbon. Everything in the world is made out of what? Carbon. Carbon, and then we take tungsten. We take carbon and tungsten comes out of this rock. Actually, if you look at that gray line going through this rock, that's tungsten. Primarily mined in China. You ask why we manufacture there? Because we need their tungsten. It's a symbiotic relationship, right? Okay. So, huh?
Yin yang.
Yin and yang, exactly. So what happened to my Rice Krispie treat? Okay. So I take the carbon and I take the tungsten. I make the hard molecule, which is the Rice Krispie. It's the wear resistant. Then I take cobalt, and cobalt, another word for cobalt you're going to hear is what? Binder. You will hear that as the years go on. It's called a binder. It holds everything together. It's the marshmallow. Now, real quickly, there's two types of carbide. Wear resistant and tough. You can't be both. Because if I'm wear resistant, if I'm really wear resistant, it's a hard piece of carbide. What's one of the hardest materials? Diamond. What's another hard material? Is glass hard? It's right up there with diamond. Diamonds are a little bit harder. Now glass is very, very hard. The the easier it breaks. It's also very, very fragile. But if I took a cutting torch to a piece of glass, it would melt, but it would take a long time, right? So hard carbide is very, very, very wear resistant. It can take a lot of heat. But if I hit it with a hammer, it's going to break. So what do I add more of? Rice Krispies or marshmallow to make it tougher? Marshmallow or cobalt. You'll hear them people say, I add more cobalt, I make bigger grains of Rice Krispie, I get a tougher grade of carbide. When I say tough, I'm thinking about rubber. It can take a licking, interrupted cuts, a lot of vibration, a lot of movement in the tool. Huh? It's not hard, so it can't take a lot of heat, but it's very, very tough. So tough carbide, you have to run slower. Hard carbide, you can run faster. You always want to run the hardest carbide grade you can without it breaking, because that means you can run as fast as you can, which is the most efficient. It's all about how many parts can I put on the floor in a minute. That's all I care about. That's all your boss is going to care about, right? So that's the basic idea of carbide. All right, now let's get into cutting tools. Every cutting tool, whether it be a drill, whether it be a turning tool, okay, whether it be a milling cutter, and for some reason I have no milling cutters. No matter what kind of tool it is, a drill, a mill, a milling cutter, a reamer, doesn't matter. All cutting tools have three angles. They are the lead angle. Now this is turning. It's the rake angle. And it's the relief angle. Now when I look at this turning tool, this is a turning tool and I've got a chuck and I'm machining a part. Which way am I feeding this tool? This way or this way? This way, right? All right, so this would be the lead angle. It's the front, it's how the tool attacks the part. And you can change that lead angle by changing this tool holder, right? The different types. Or you're using manual machines, so what do? You just turn it in, you just change it in the compound. But when you have a CNC machine, you actually got to get a different holder with the pocket milled in differently. All right? For a drill, half of this point is my lead angle, because this is what hits the part first. Make sense? If I had a milling cutter, pretend I'm the milling cutter, and this is my insert, right? Out here on the periphery. If I'm milling in this, my spindle's up here, right, like a Bridgeport. I'm milling in this direction. This would be my lead angle, right? That would be 90 degrees. That would be a heavy 45-degree lead angle, right? That would be a negative 40. Well, we wouldn't talk about that. I kind of did the wrong thing there. So every cutting tool has a lead angle. Why do I care? Why do I care? How efficient the tool is, it's not that. One of the things that I said too, what did Obi-Wan tell Luke to do with the Force? Use the Force. How do you know how to use the Force? Cutting forces are always perpendicular to the cutting edge. 90 degrees, right? That's what perpendicular means. I can't change the amount of force being created, but I can change the direction. If this is the direction of the force, that's perpendicular to my hand, right? If I change the direction of this on this turning tool, right now that force is going this way. If I change that by changing my compound rest in the manual machine or this tool holder differently, I can change where those forces go. Why do I want to do that? I want to push them to where my setup is most rigid. Okay. I can do that with this. In a drill, I'm going to have to change the drill point. Okay, in a milling cutter, I'd have to get a different, if it's indexable, I'd have to get a different milling cutter to change that angle. But I might want to do it to change. If I'm hanging my cutting tool out this far, what's going to happen typically? It's going to chatter. You know how to stop that? I can only make it so rigid, right? But if I take that cutting edge angle, because if I, end mill, let's say this is an end mill, right? And it's hanging way on down. That cutting force is perpendicular to that cutting edge, right? But what if I take that cutting edge and I lay it out flat? All those cutting forces are going up into my spindle and down into earth. Okay, they're called high feed cutters. So by changing the direction of that force, I can eliminate that chatter. I can't take a big depth of cut, but I can move really, really fast because I don't have any chatter. Okay, so as I said, cutting forces are always perpendicular to the cutting edge. This is a 0-degree turning tool, perpendicular. Again, my cutting forces on and lead angle on a drill is half the drill point. Again, it's perpendicular to this cutting edge. If this was a milling cutter, rotating this way, again, perpendicular to the cutting edge. If I change that angle, I therefore change the force direction. Now, here's something else that they don't teach all the time. When I change that lead angle, not only do I change the direction of the force, I actually thin the chip. How many of you are really into geometry? Right? You need to get, that's the one thing that I could actually get. I couldn't get algebra. Stunk it in. But geometry, because there's pictures, it's better with pictures. I can actually get it. What happens, and let me show you, I will illustrate what I mean. Don't try this at home. Change to a cheaper paper. Okay, I can do it that way.
Norman, the commercial would say this is a professional doing this, but I can't say that.
Yeah, don't do this at home. This is the time you might want to turn off the camera. No, leave it on. All right, so if I look at this milling cutter right here, right? If this was a square shoulder, if I fed this 10 thousandths per revolution, how thick would my chip be? 10 thousandths if it had one insert. Now, if this is 10 thousandths, right? And this is a 45-degree lead angle, now look how thick my chip is. It's geometry. It's trig. When I change that lead angle, the total area of the chip is the same. It's going to take the same amount of force. The total amount of material I'm taking is the same. But the chip gets thinner. Why do I care? I change the force. It's all about money. If I thin the chip, you think I can feed it a little harder? Because now, my forces are going, instead of being totally, if it's totally on my end mill trying to push it to the side, if I change the direction where it's split between the spindle and the ground, I'm more rigid. Plus I got a thinner chip I can feed faster. Let me ask you now, what do you think it take to make a chip? Said it on the first two slides. One of them is, one's heat and pressure. What two things wear out carbide? Heat and pressure. Remember yin and yang? Can't be too hot, can't be too cold, it's got to be just right. Where do I want the heat to go? In the chip. In order for it to go into the chip, I've got to have a thick enough chip for it to go into. If my chip is too thin, what's going to happen? It's going to go into the part. The part's going to grow. And you're going to get yelled at by the inspector because when it goes into the air-conditioned inspection room where he works, it shrinks. It'll be undersized. Where else does the heat go? Into the tool. What two things wear out carbide? Heat and pressure. So it's that yin and yang. So, as you change your lead angle, you can change your feed rate because you have a thinner chip. All right. Now, there's a thing called the rake angle. All right. If this is my turning tool holder, now, how many of you like this chip? Your boss would? See, you wouldn't be necessarily a good boss. Alright, because I didn't want that in public. Okay. You want us to, can I get your name? Your boss number?
Wait,
Why
I'll turn that off.
Why do I not like this chip? This is a dangerous chip. It's nice and thick and it's nice and wide. It's a big chip, but it's also unruly. You can't manage this chip. What shape do you want your chips to be? 6s, 9s, or C's. And I'm going to tell you something too. You don't want them real tight, guys. Everybody thinks real nice tight ones are good. No. You want those chips to be as open as they are before they can start doing this. Because if it's too tight, it's too much heat and pressure and you're wearing out your tool. And every time you have to index your tool, here's the truth. It's not about the tool cost. Your time is worth more. That machine time is worth more than the tool. If you're making an engine block, what percentage of the cost of making that engine block is tooling? What do you think? 5%? How many of you think he's too high? Anybody? You think he's too high? How many think he's too low? What do you think it is? Huh? 8? Anybody else want to try? You say 10 now. You're conflicted, aren't you? You need to learn to stick with your gut because you were close. You won? Actually, it's 3 to 5 for most materials, common materials. I'm not talking about your nasty stainlesses or your high temperature alloys. I'm talking about standard steels, high-low carbon, your standard cast irons. It's 3 to 5%, typically on the 3 side. For high temperature alloys, Hastelloy, Inconel, Waspaloy, titanium, it's closer to 7 to 10 because they like carbide. Because they're called refractory metals. They laugh in the face of heat. So my point is, when you're wearing these tools out too quickly, you don't want to wear them out too slow, you don't want to wear them out too fast. You want to be just right. Because it's not about the price of the tool. It's about the price of making parts, having the machine running. On this tool, if I was turning and going into this direction, the rake face is the surface of the cutting tool that the chip rakes across. Make sense? So if you looked at this drill, it would be here, right? On an end mill, it would be on this flute, right? Because that's what's cutting. So it's this way. On the drill, it's this way because the cutting edge is up here. So it's here. But if it was a mill, it would be here. I was cutting on the side. Make sense? Now the rake angle controls the strength of the cutting edge, and it controls the amount of pressure or cutting forces being generated. And I got 2 choices. You've seen tools that are presented, and this is an exaggeration. That's a negative cutting edge if I'm cutting in this direction. Okay? If I was or you'll see a cutting tool that will be like this. That would be considered positive, right? All right. Which one's stronger, the one on the top or the bottom? Is this stronger than this? How many think this is stronger? Raise your hand. Okay. How many think this is stronger? Oh boy, we got some work to do. This is actually stronger. Cutting forces are always what? Perpendicular. My cutting forces on this tool are going this way. That's nice and thick. It's strong. It also creates a lot of force. Cutting forces are always perpendicular. What's behind this? Now which one do you think is stronger? When you look at it that way, it makes sense, doesn't it? This one is freer cutting for your soft gummy materials. You want that positive cutting edge to shear the material off. For your harder materials, you need more strength. You want to push the material off. Make sense?
Okay, guys in the first row, you guys with Dave, remember what he said about how does carbide like to be? In tension or compression?
Compression.
So So your top, you're squeezing that carbide together.
This is in a state of compression. This is in a state of what we call transverse rupture. It's a fancy term that carbide doesn't mind being like this. It doesn't like being like this. If you've got something underneath it supporting it. Now sometimes you've got to do this, sometimes you got to have something like this for aluminum. If you try and push aluminum, it's going to push back. It's not going to cut very well. It's going to smear and be nasty. So depending on the type of material, you have to change the type of rake angle you have. I got hard and tough carbide. Now I got different rake angles, and I got different lead angles. Lead angles where the force goes, and this is how I shear the material. How am I doing, boss? Good. All right. So when we look at it, if this is a cutting tool, this is my chip. What's happening is there's 3 shear zones. Here, this is where the material is being plastically deformed and sheared away. You saw it in the movie, right? Here's where it starts to slip on the rake face of my cutting tool. This is negative, this is positive. Make sense? Now here's the part you may not understand. When your cutting tool is coming across the material is actually saying, I don't think so. It's backing out of the way. I don't care what kind of material it is. All of them move somewhat. Soft gummy materials, they call it modulus of elasticity. It's a fancy word that means it just moves out of the way and then comes back. Now, what's your name? If I want to beat up Jamie, right? And he keeps dancing around and moving out of the way. How do I get a punch in? I grab hold of them and I pull them in, right? So if my material's moving out of the way, what do you think I want? This or that? The bottom one. I got to pull it in. Soft gummy materials. It makes sense? Now, if I got a material that's real hard, it's putting a lot of forces on my cutting tool, causing it to want to break, I go to this one. All right. Now, carbide, okay. What 2 things it take to make a chip? Heat and pressure, but it takes a certain amount of heat and pressure, right? If I do this, eventually my hands are going to get what? Hot, blistered, right, warm. I want to be able to control the amount of heat and pressure at the shear zone. So the last angle is what I call clearance. And on this tool, if it was setting this way, right? You can barely see it, but this tool is tilted 5 degrees in that pocket, which means when I'm cutting, this edge is tilted 5 degrees. So it's got clearance so it doesn't rub. If I look at this drill, okay, I'll take the insert out. If I'm holding this straight, you see that this edge is tilted down right here, right? That's so this edge does not rub. This cuts right here. That's the clearance on my drill. All cutting tools have it so they don't rub, because I will need to be able to control the amount of heat and pressure at the shear zone. There are 3 primary cutting forces. Tangential. Well, what tangential is, when in turning, where my part is turning, I've got a major amount of force on the rake face or top of the cutting tool. It's causing my tool to want to deflect. That's 70% of all the forces being exerted. 20 to 30% of my forces are feed. And the smallest force is radial, the part trying to push against the tool. Now, of those 3 forces, which one's the biggest pain in the butt? You would think it's tangential because it's 70% of all forces, but it's not. Now you went the other way. It's radial. If the cutting tool and the part are pushing away, what eventually happens? They come back. And they push away and they come back. They push away and they come back. What's another word for that? Chatter. Chatter causes bad finish, it causes size control, it causes chippage. You were thinking something else, get that off your mind.
It's for.
Oh, chatter?
Where we work.
You got chatter?
Chatter?
There's ways to check, there's ways to fix it.
Oh, we can't do that.
There's ways to fix it.
Too much time.
Well, it takes time to fix, yeah. Well, here's the truth. Here, and you guys may be too young to remember this. There was a time that Japanese companies were known for better quality cars than we did. When was it? During the 70s and 80s? Late 70s and early 80s, I wouldn't buy an American-made car. Because quality stunk. Japanese was better. Why do you think they were better? Actually, it's because of the acts of two Americans, Demi and Duran. They were quality gurus. They were Americans. After World War II, we wouldn't listen to them, so they went to Japan and taught them how to rebuild and do it right. In Japan, what they did is they would not put it out on the shop floor unless it was right. In America, what do we do a lot of times? Just get it out on the shop floor. We'll make it work when it gets there. We'll make it work. We make it work, then what do we do when we're done with the job? We forget about it. We move on to the next fire drill. It wasn't until recently, in about the late 90s, early 90s, that we started paying attention to it and brought those things back. It cost a little bit more up front, and I know not all the bosses are going to do that. It costs a little bit more up front, but it pays big dividends in the end. All right, what do you think carbide likes to do? It likes to cut. What does it not like to do? Rub. Rubbing's for what? Rubbing's for what? Redneck? Huh? Is that what you say? Well, if you consider rednecks guys who like racing, have you ever heard the term rubbing's for racing? Okay. Rubbing's for racing. That's the first time I've ever heard rednecks. Like,
Hey, Days of Thunder is going to be an old movie now.
I guess it is. You guys probably don't remember that movie. I am getting old. Oh, there it is. All right, rubbing's for racing. It ain't for carbide, because if you're rubbing too much, I got to control the amount of heat and pressure. Do you have a football? You get one for rednecks. I might have to give you another one. All right. It takes a certain amount of heat and pressure at the shear zone. If I'm rubbing too much because my clearance angle is wrong, or I got too negative a tool, I'm creating more heat than I really want. That heat's going into the part. So look what happens. Look what happens. Here's my cutting tool. Right here's my cutting tool. Here's my part. What am I doing here? Rubbing. Now, I want you to watch the structure, the crystalline structure of the material as it starts entering that rubbing zone. What's another word for that? Work hardening. During the first Gulf War, we had A-1 Abrams tanks flying across the Iraqi desert, and they were falling apart. The bolts were breaking. Two main reasons. One, they were using the wrong insert. They were using a partial profile threading insert. In other words, it had a sharp point when it should have had a radius at the root. The second reason, they were taking spring passes. How many of you take spring passes or have heard that term?
Goes past the zero pass.
Goes past, zero pass. All you're doing is rubbing. Carbide likes to cut. If you're doing stainless steel or any kind of work hardening material, and you do spring passes or ghost passes, this is what you're doing. Between that sharp edge at the root, the work hardened surface, they were snapping off and breaking. Okay? Carbide likes to cut. Typically in the United States, we take a 10 thousandths finish pass. Me, myself, and I would never take below my nose radius. If it's a 32 thousandths nose radius, I take a 40 thousandths finish pass. And believe it or not, it's easier to control size. How many of you run a manual machine? How many of you ever tried to sneak up on the dimension you're trying to get on that class project? Next thing you know, you go undersize on the last pass. The reason being, are machine tools perfectly rigid? No, they've got play. When I'm taking 100 thousandths or 150 or 200 thousandths roughing pass, I'm really putting that play to work. Then as I start doing successively smaller, that pressure starts to change and get less. When I just take a nice little light cut, it sticks it. I don't have that force from that heavy depth of cut, keeping them separated. Does it make sense?
Isn't that really like your spring cut?
You don't want a spring cut. That's my point. If I do spring cut, I'm going to get this. Spring cut means I have to make 2 cuts. I don't want to make 2 cuts. I want to hold size, 1 rough pass, 1 finish. And if I did it my way, I'd just do 1 pass and finish it all at one time. The only reason I can't do that is sometimes the finish requirements won't let me do that. There are ways to get around that as well. Or the machine. I agree. I agree. But carbide likes to cut. Here's the other thing. It changes the direction of my cutting forces. I've got a very, very thin chip because it feathers out around the nose. My tool's going to burn up a lot faster as well. I got my cutting forces going in the wrong direction. I want them to go into the spindle instead of this way. I've got a very, very thin chip which is putting my heat in the part and in here instead of this chip because that chip feathers around that corner. It goes like this. I got nowhere for the heat to go. Productivity versus tool life. A lot of people say they want their cake and eat it too. I'm one of those. You've only got 3 things to play with when it comes to tool life and productivity. You've got speed, you got feed, and you've got depth of cut. Speed, feed, and depth of cut. When it comes to productivity, these are ratios. It's a 1-to-1 ratio. If I increase my speed, feed, or depth of cut 10%, what happens to my productivity? Does it go up or does it go down? Productivity. If I increase my speed 10%, what happens to my productivity? Up or down? Up. How much? 10%, same amount. Same's true for my feed rate. I increase my feed rate 10%, my productivity goes up 10%. Depth of cut 10%, productivity 10%. Now let's look at tool life. As you notice, the ratios aren't the same. If I increase my depth of cut 100%, what happens to my tool life?
It drops.
Take a look at the ratio again. What's the ratio? It's 1 to 0. Depth of cut is free. Once you reach a depth of cut 10 times your feed rate, so if my feed rate's 10 thousandths of an inch, once I reach a depth of cut of 100 thousandths, anything more doesn't cost me a dime in tool life. It just gives me productivity. Depth of cut is free. Always maximize your depth of cut. If you have the rigidity of the part, of the machine, take as much as you can. Eliminate passes. It doesn't cost you a dime in tool life. When we're optimizing an operation, you always maximize the depth of cut first. Now, if I increase my feed rate 10%, look at the ratio on tool life, what do you think happens to my tool life? Does it go up or down? What do you think it does? I'm generating more heat, so is it going to go up or down? It's going to go down. If I increase my feed rate 10%, my tool life goes down 10%. If I decrease my feed rate 10%, my tool life goes up 10%. It's opposite. Now when you look at speed what? You always hear it, speed what? Speed kills. Now remember, we give you a surface footage in the book. I'm saying you're running within that surface footage. If you go below what we tell you in the book, that's like trying to jump out of a closed window. You're not in the window. If you go above what we tell you in the book, it's like you want to be within that window that we tell you in the book. But speed kills. I increase my speed 10%. My tool life goes down 20%. So what you do always, take the maximum depth of cut first. Take the maximum feed rate second. And then put the speed in the range that we give you in the book to where you get the tool life you want. That's how you optimize an operation. That's how you get the most for your cutting tool and the most out of your productivity. There's 3 basic machining operations. Turning, milling, hole making. I'm not going to get into those because you already do this for a living. How many of you actually have jobs doing this for a living? How many of you the rest of you just do it at school? Huh? You had a job? Okay, I'm not going to get into this because you've seen it. You know what a Bridgeport is. You know what a lathe is. You know what a CNC lathe is, and you know what a manual milling machine is. So, what 2 things does it take to make a chip? Heat and pressure. How do I control the heat? Speed. How do I control the pressure? What 3 elements are in carbide? Carbon, carbon, and tungsten. Tungsten, carbon, and cobalt. What 2 do I combine to make the hard Rice Krispie or the wear-resistant particle? No. Cobalt is the what? Cobalt is, what's another word? It's the binder. It's the glue. It's what holds everything together. So what 2 make the Rice Krispie? Carbon and tungsten. What are the 3 cutting angles that all tools have? Rake, lead, and relief. What else do I have? What are the 3 cutting forces? Forces. Tangential, feed, radial. Okay. All right. You want to stop that?
Chris, they listen to that one to you? No. When they're away,
When they're away? All right, you want to stop that and start it again? Any questions about that section? That is the first section that we teach out of that book all the time. It's the basics. We reinforce that through every other section in that book.